Okay, so we want to first state von Kamppen's theorem, which relates the fundamental group of a covering of a space to the fundamental group of the space, right? And it will be a useful tool in computing fundamental groups. In particular, it will allow us to compute the fundamental group or describe the fundamental group of all surfaces, all compact surfaces, all compact two manifolds. Okay. So we discussed the notion of the free products between two groups. Is that clear? Right. And then we have this, it's called the universal property of the free product. And it says the following: if I have a collection of groups, G alpha, and a collection of homomorphisms of groups for each alpha, I have a phi alpha from G alpha to some fixed H, then I can put all of these together in a unique way to obtain a homomorphism from the free product of the G alphas to H. Is that clear? If I have homomorphisms from all of these groups to a fixed group, then there's a unique extension to the free product. Is that clear how you would define it? On any word, so remember, elements of the free products are given by words where each letter or each symbol GI is an element in one of these groups G alphas, right? So on any word, I can define this map phi to be phi alpha 1 applied to G1 multiplied by G alpha 2 applied to G2 all the way up to phi alpha M of GM, where by alpha I mean the index of the group containing GI. You just apply the corresponding map to every GI and multiply them all together. So, is that clear? Okay, so let's go to the statement of von Kamppen's theorem. So there's, okay. I think something got erased here. I'll explain. Maybe I can do this. Just a second. So U U comma V comma U cat V. Okay. U cap V is the intersection of U and V. Okay, so the statement of von Kamppen's theorem. Oh, I'm not recording, sorry.
Yeah, you are.
Oh, I am. Okay, good. The statement of von Kamppen's theorem is the following. So let X be any topological space. And suppose we have a covering of X of two elements, two open sets, U and V. So U and V are open sets in X, and they cover X. So the union is X. So we want to say something about the fundamental group of X in terms of the fundamental group of U and the fundamental group of V. Okay? So we're going to assume that U, V, and the intersection of U and V are path connected. And let's choose a base point x0 on the intersection of U and V. So x0 is in U, x0 is in V, x0 is in X, therefore. And I'm going to denote by JU the map the map at the level of fundamental groups induced by the inclusion map from U to X. Right? I'm omitting the base points of the fundamental groups, but it's always x0, right? That's why I fix x0 here. But I'm omitting it in this notation for simplicity, okay? So JU is induced by the inclusion from U to X. JV is induced by the inclusion from V to X, and this is supposed to be pi 1 here. Pi 1, how do I do this? I don't know. Pi 1. This pi 1 of X, I'm sorry. Okay. So JV is induced by the map from V to X, right? And similarly, we have IU, which is the map on the fundamental groups, induced by the inclusion from intersection of UV into U. And similarly, IV is induced by the inclusion from the intersection of U and V into V. Okay, so this is the setup, just notation. Then the statement is the following. The map phi from the free product of the fundamental group on U and the fundamental group on V, these are the two pieces, U and V. I can look at the fundamental group of those two pieces. I can take their free product. And there's a map from that free product to the fundamental group of the space X. That map is induced by JU, which is a map from pi 1 of U to pi 1 of X, and JV, which is a map from pi 1 of V to pi 1 of X. I'm using this property that I described above for the free product, right? If I have maps from each piece, from each group into a target fixed group, then I have a unique map from the free product. So the first claim is that this map is surjective. What does this mean?
I have a quick question. So when you say like, so I'm assuming like when we take this when you say it's induced by these two maps and you're taking the free product, like component wise, you're going to take, like you said earlier, like if the elements in pi U, you're applying JU on it, and then
exactly
our free product with if it's in V, right?
Exactly. So let me write it here. So if you take phi of, I don't know, G1 GK, right? It's a product of things. How do I apply this V? Well, I have to look if GI lives in U and V, and depending where it lives, I use the corresponding J, right? So I'll just write it like this, because I don't know which, you know, like I'll omit the index. So yeah, I'll omit the notation, the U and V here. But of course, this is U if G1 lives in pi 1 of U, or V. This would be V like that if G1 lives in pi 1 of V, right?
Okay.
And then you can take their product because all of these are elements in pi 1 of x, right? And you can multiply them.
So then I guess, like, if you have like an element, we're not going to have issues with elements in the intersection though, right? Like there's no ambiguity.
No.
Okay.
Well, but we'll get there. This point
Okay.
will be explained clearly. Yeah. I mean, you can say something about the intersection. Yeah.
I'm just saying that like JU on an element of the intersection should be the same as JV on an element of the intersection.
Yeah. Of course. That it follows because, I mean, if you include the intersection into U and then include it into X, is the same as including the intersection into V and then including into X. So the maps induced at the level of fundamental groups agree if you started the intersection. Okay? So yeah, it doesn't matter, which one you use if they lie in the intersection, essentially. Does that make sense? Okay. So this map is surjective. This is the first statement of von Kampen. I think this is the one we're going to concentrate on today. Okay. The second one is describing the kernel of phi explicitly. Right? So what does it mean that this map is surjective? What's the intuition? It means that if you have a loop in a class of a loop in pi 1 of x, then what?
You can break it down into a sequence of loops in U and V.
Exactly. You can break it down into a word, namely a sequence of loops of this form, G1 ... up to GK, where each GI is a loop in U or a loop in V based at x0. The base points of all of these fundamental groups is x0, right? Does that make sense? It's not completely straightforward to prove, right? Think about it. You have a loop in X, and you have these two open sets U and V. How can you prove that this loop in X breaks down as a multiplication of loops in U and or loops in V? It's not completely straightforward. I mean, yeah. If you think about it for a few minutes, I think you'll be able to come up with your own proof. We'll prove it formally today. Is it clear?
I have a question. How do we, and maybe this will be more obvious when we do the proof, but how do we deal with the case when the loop in X, like it starts in U cap V, and then it goes into just U and it goes into just V before coming back? Like it spans both U but not V and V but not U. How do you decompose that into a loop that's just in U and a loop that's just in V?
You can take the trivial loop, right?
No, wait a second. I think I didn't follow your question. Can you ask it again one more time?
So in other words, there's X has like three sections, right? The part that's just U, the part that's U and V, and the part that's just V.
We'll see a picture soon, but keep going.
So how do you deal with the case when a loop starts in the part that's U and V, goes into the part that's just U, and then also goes into the part that's just V?
If you start in the intersection of U and V, you go to the part that it's on U, you said?
Yeah, so in X minus V, and then you go to the part that's in X minus U. So that one loop covers, like, goes through both of those parts of X. How do you break that?
Yeah, the point is that you can break down this loop. That's what we're gonna show. We'll break it down such that different sections stay where you want.
Okay, so it won't necessarily be the same.
It will not be the same loop. Remember, we're working up to homotopy.
Oh, right, okay.
These are homotopy classes of loops. So we have some freedom.
I see.
Yeah, so we'll break it down. But the problem when you break it down is that each piece will not be a loop, right? It will just be a
Right.
path, but it will not be a loop based at x0. Does that make sense?
Yeah.
Like if you break it down so that they stay where you want, then you have broken it down into paths, which are not necessarily loops. So you have to deal with this. So how do you deal with it? You choose a path to the base point and then go back through that path again, making each piece a loop.
I see.
You'll see a picture in 2 minutes, but it's good to like try to think about it before seeing the picture.
Okay, that makes sense. Thank you.
Yeah, like you add a whisk from the endpoint of each piece to the base point using the path connected property, you'll see, and then go back through that same path, running it backwards, and that makes each piece a loop, okay?
Right, okay.
We'll see a picture. Okay, so that's the first statement of Van Kampen, that you can always break down any path like that. Any loop in X, any homotopy class of loops in X can be broken down into a product of loops, each lying in either U or V, or both. Okay. There's a version of this theorem of Van Kampen for coverings with more than 2 elements. Okay, and we'll state it later on. The proof it will be exactly the same argument, but it's easier to write down the proof when the covering has 2 open sets. Okay. Okay, so that's the first statement of Van Kampen. The second statement is a description of the kernel of phi. Right, so the statement is that the kernel of phi, in other words, everything that gets mapped to the identity by this map phi, is the normal subgroup of this free product generated by the words. So these are certain words in this free product. So words IUG inverse times IVG inverse. So recall IU and IV means that they come from the intersection, right? IUG mean that it's a loop coming from the intersection, all right? Loop in U, homotopy class of loop in U. And IV, similarly, homotopy class of loop in V coming from the intersection. So the kernel of phi is a normal subgroup of the free product generated by these words, where G runs through any element in pi 1 of the intersection. So let's digest this a little bit. First, is it clear what I mean by the normal subgroup of some group generated by certain elements? Can anyone explain what this means more precisely?
Can you repeat that?
Yeah. Can anyone explain what this phrase means? The normal subgroup of a group, in this case, this free product, generated by some set. This is a set, right?
Oh, yeah.
What does that mean? The normal subgroup generated by a set. You have a group here. Maybe let's call this G for simplicity. So you have a group. You have a group G here. This is G, right?
Oh shit.
You have a group G. And you have a set, which is all of these words of this form. IUG inverse, IV inverse. What does it mean to take the normal subgroup generated by a set inside a group? Can
Well,
someone?
like it's
Yeah.
it's just a set, so you need to include like inverses and stuff. So you need to make it a group first, and then you have to include like its
Yeah,
conjugates so that you can get normal.
Right.
Like
Exactly.
get normal as an unnormal subgroup. But I think formally they define it as like the intersection of all subgroups of the original group, the larger group,
Right.
containing that set.
Correct. That's a correct definition. And we think of it as you take the set, right? In this case, these guys, IUG inverse IVG. That's a set of words in this free product, right? You take that set and you consider all conjugates of this set by elements in G, right? And then you consider all possible products with these guys. And that's the normal subgroup that that's generated by a set, right? It's like you take the smallest normal subgroup containing that set. That's what it means. The smallest normal subgroup of G containing that set. In this case, this set running through all G's in pi 1 of the intersection of U and V. Okay? So we will not prove this part today. We'll prove the first part. But I mean, you should convince yourself that this is easy to see, that this all elements like this are inside the kernel of phi. Do you see that? What do I get when I apply phi to this? Let's do it. When I apply phi, I'm applying phi to IU G inverse IVG. What is this? How do I apply phi? Do you guys remember?
Yeah, so you apply, well, it's a homomorphism of groups, so you can like distribute across a product, right?
Well, that's the definition of phi, right? Remember,
Okay, so you'll apply like J
yeah.
U on G.
J
The first thing.
U, right? IU, RU on G inverse, right?
Mm-hmm.
Times JV IV G. Correct? You just apply the corresponding J's to every term in that word. Oops, what's this 9 going here? Okay, good. But what's this? What's JUIU and JVIV? Those are the same map. Remember? This is what I said earlier in response to a question of Sophia. JUIU, that's the map that first applies IU from the intersection U and V to U, and then applies the map induced by the inclusion from U to X, which is JU. That's the same as the other map if I start with IV and I follow it with JV.
This should be the identity then, right? The element, I should say. Like if you, because you'll end up with what, G inverse times G, right?
Not the identity. This will be the same element. So I can write this. Let me do it like this, maybe. IG. I'll explain why it's not the identity. IG maybe let me use another letter instead of I. I think I is fine. I'll explain why I is in a second. This is the same as this, where I is the map, where I is induced by the inclusion u cap x in u cap v into x, right? That's what I mean.
So this inverse, I'm a little unclear. Is it the inverse of I or the inverse of G?
Does it matter?
It's an inverse element. It's not like a pre-image.
No, it's yeah, it's the
It's the inverse of the image, isn't it?
yeah, but it's that's the same as the inverse of, I mean, it's a group homomorphism, all of these maps, right? So it doesn't matter if you put it outside or inside the G. It's
yeah,
not
it's
an inverse.
an inverse element.
Yeah, it's not an inverse image. It's an inverse element, right? Does that answer your question? I can try it and explain
I'm
again.
not sure, to be honest. It
Yeah.
might answer the question. I just don't understand it.
Okay, let's go slowly. What's your question again? What does this inverse mean, right?
Yeah, what are we applying it to?
Right. So G is an element in a group, in this group,
Got it.
right? IU is a group homomorphism. See, IU goes from
Yeah.
pi 1 of u intersection B to pi 1 of u. That's a group homomorphism, right? So IU of G is a group element in pi 1u.
Okay. So this is the
inverse of that
inverse
group
element of that element.
Yeah, exactly.
Okay. I
Okay.
think that makes sense.
Yeah. And now I'm saying all of these elements are in the kernel of phi. That's my second claim. And that's straightforward from the definition of phi. So let me explain. If you apply phi to this element, for example, what does that mean? So this element here lives in pi 1 of u, and this element here lives in pi 1 of v, right? So applying phi to this word, just a second, I need to run and get my charger. Okay, I'm back. So I was explaining that these elements, IU of G inverse, IVG, are in the kernel of phi, right? And when I apply, why is that? Because when I apply phi to it, by definition, that means applying JU to the first term and JV to the second term. So that's this line right here. But JU composed with IU, it's the map induced by the inclusion from the intersection of UV into X. So I is a map, I should write, I is a map from pi 1 U cap V to pi 1 X. Induced, yeah, induced by this inclusion. And these are the same, right? Why are these the same? Because they're induced by the same map. The only difference is that you're factoring this map through U or factoring it through V, but that doesn't matter. You started in the intersection.
I'm still not sure why like IG inverse times IG isn't collapsing.
Oh, it's collapsing. Yeah, I mean, IG inverse times IG, right? So there you go. Yeah. My claim was that I is not the identity map or anything like that. Remember, the map induced by an inclusion is not an inclusion.
Can you say that again?
Yeah, the map at the level of fundamental groups induced by an inclusion of spaces is not injective. It's not necessarily an inclusion map. Right? If I have an inclusion of spaces, A into B, an injective map, right? The map from pi1 of A to pi1 of B doesn't have to be injective.
Yeah, you needed like a deformation retract or whatever, right?
Retract,
For it to-
yeah.
Yeah.
Does anyone have a quick example in mind to remember to remind
Yeah,
yourself?
it was like R into, or no,
Even
it was like S1 into R or
Yeah,
something like
yeah,
that, or R2.
S1 into the disk.
Oh, okay, yeah.
That works as well, right? S1 has fundamental group Z, but the disk has no fundamental group. So even if the map from S1 into the disk, the boundary map, is injective, when you pass to fundamental groups, you have a map from Z to 0, which cannot be injective, right? So anyway, we'll talk more about this second claim on Monday. So let's focus on this claim in the remaining 10 minutes. We want to prove that every loop here can be written as a composition or a free product of loops in here, right? A word of loops in which each loop is in U or in B. So let's prove that. By the way, why is this von Kampen useful? Well, because phi is surjective, right? So this means that I have an isomorphism between the fundamental group of X and this quotient, right? By the whatever first isomorphism theorem or something for groups. So if I can describe pi1 of U, pi1 of B in this kernel, then I can describe the fundamental group of your space, right? And it's often the case where pi1 of U and pi1 of B are relatively easy to describe. Okay? So let's prove the first claim that this map phi is surjective. So suppose F is a loop in X based at X0. And we use the Lebesgue number lemma to obtain a partition of the interval 0, 1. Let's call that partition given by numbers S0, S1, all the way up to Sm, right? Up to 1. So we can obtain a partition so that F maps the closed interval from Si to Si plus 1 into U or V. Do you guys see how I'm using the Lebesgue number lemma? So let me be a bit more precise. So U is covered by U and V. Sorry, X is covered by U and V, right? X is covered by U and V. So if I take the pre-images of U and V along F, I get a covering of 0, 1. So the Lebesgue number lemma tells us that since 0, 1 is compact and it's a metric space, you can always cover it or partition it into small enough, in this case, small enough intervals, such that each interval gets, each interval lies inside the inverse image of U or the inverse image of V, which is exactly the same oops, the same thing I've said here. Okay, so that's the use of the Lebesgue number lemma. So now let f restricted to si, to the interval si to si plus 1 be fi. This is just notation, okay? And now I'm going to consider the loop obtained by multiplying all of these pieces, f1 up to fm, right? This is the same as f, although not quite the same, because how do I define this multiplication of loops? Remember, I split it at 1/2 and so on. So it's homotopic to f. It's off. It might be off by a reparametrization. Is everyone following? Or did I lose you guys? So I found this partition of the interval such that each piece lies inside U or V, each piece of the loop, right? So Fi is a path now. It's a path, a piece of your loop, which lies inside U or V, right? And then F can be written up to homotopy, right? It's almost the same, right? The problem is, I mean, it's the same. The problem is that how I define this multiplication, by definition, I use 1/2, right? But these are off by a reparametrization. The image of the loops is the same in your space, right? So I've written F as a product of paths. So this is wrong, right? I wrote this wrong. It's not a loop. It's a path. Might not be a loop in U, right? So this is a path. This is a path. Path in U or V, right? And now, this is related to one of the earlier comments. So without loss of generality, we can assume that the subdivision is chosen such that each endpoint of each of these paths, Fi, namely Fsi, lies in the intersection. I'll explain why we can assume this in a second. So this would mean that each of these Fi's are paths that start and end in the intersection of U and V. And I can assume this without loss of generality. Namely, if my partition does not satisfy this, I can always find another one which satisfies this property. And let me explain it in a picture now, okay? So there's a picture of an example. Suppose I have X, which is covered by U and V, right? And I have my loop F, which is this composition of, I mean, it's like the green loop, the green path together with the blue path, that's F. And I have found a partition such that each piece lies inside U or lies inside V, right? I have 8 pieces here. But I'm saying with a loss of generality, I can assume that all my pieces start and end at the intersection, right? For example, if my subdivision splits my loop, my green loop into these 4 pieces, I can change the subdivision such that these F1, F2, F3, and F4 are actually correspond to the same interval in the subdivision, right? I kind of erase these points, these subdivision points that do not lie in the intersection, right? So I can substitute the partition by another partition that would give me a picture like this. In this case, I start with 8 pieces, and after this, this removing certain elements in the partition, certain partition points, I get only two pieces in this picture. So I can always assume I can break up the path. I can break up the loop into paths that start at the intersection and end at the intersection, like that.
So basically, because you have to pass through U and V,
Exactly.
or U intersect V in order to go from
Exactly.
U only to V only, you can always
Exactly.
partition this one.
Exactly. That's exactly the idea, right? You have to pass through U and intersection V to get to V, from U to V. Yeah. Okay, so we assume we're in this setting, right? Of course, it doesn't have to be two loops, right? Like this can keep going like that, and then F2 doesn't have to end in this endpoint, in this base point X. It can end like up here, and you can continue with another loop like that, and another loop like that, and so on, right? But in this picture, for simplicity, I just have two loops. Okay, I need 5 more minutes. So now, what's the problem with this picture? I split my loop into pieces such that each one lives in U or V, but there's a problem that these pieces are not loops. Remember, in order to prove that phi was surjective, I wanted to give you loops in U as like a decomposition of your loop in terms of loops in U and loops in V. But F1 is not a loop in U. F2 is not a loop in V. How do I make them loops?
Just connect like that point,
Yeah.
x1 that's in the intersection to your x0.
With some path, right?
Yeah, because the intersection's path connected.
Right. We're assuming the intersection is path connected, so we may choose paths GI, a bunch of paths. In this picture, we only have one because we only have 2 loops. But we choose path GI in the intersection from X0 to F of SI, right? Which is a breakpoint. One of the splitting points, that's one of the splitting points, which by assumptions will always lie in the intersection. We show that with a loss of generality, we can assume all the splitting points are in the intersection, right? So in this picture, it will look like that, right? You can always find such a path. And now what's your new loop? Or what are your new loops? Well, instead of F1, I do F1 followed by G going backwards, right? And then I go G forward, I do F2, and that's it. And those are 2 loops based at X0, each contained in U or in V. So in general, the new loop looks like that. You do F1 first, you get somewhere, you get to the endpoint of F1, and then you apply G1, which connects you to X0. G1 backwards, sorry, that's what this means. Then you do G1 forward, and you follow by F2.
Should there be a star between F2 and G2?
There should be a star here. And then you do G2 backwards and so on, right? And you get all of these pieces here, this one, that one, that one, will be loops based at X0. Each of them contain either in U or V, right? Because the G's are contained in the intersection. And the F's are contained all in U or all in V. And this is homotopic to F. Obviously, of course. When I do G backwards followed by G up to homotopy, I can replace it by the identity here, right? Up to homotopy, right? Because I'm just doing like a whisk, like. So this is homotopic to F. So there is a composition of loops at X0, each of which is in U or V. And I'm just going to consider the homotopy classes of these things. So let alpha be the homotopy class. So there's something that might be confusing. I'm using notation. So, and I emphasize it here. So the little stars here denote loop concatenation, right? The big stars denote the product in the free product of groups, right? Which in some sense they're the same, but yeah, they're different as well. So you consider the following word, right? Each of these is a homotopy class of loops either in U or B, right? So this is a word in the free product. And then by construction, this word satisfies this, right? Since we just said this is homotopic to F. And that's the proof of surjectivity. It's not too hard, right? You just have to take into account that once you use the Lebesgue number lemma to split your loop into pieces that each of them lie in U or B, you have to take care of the fact that each piece is a path and not a loop. And you just do that using the path connectivity assumption. So that's surjectivity. So I will stop here. And I will continue with describing the kernel of this map phi on Monday. Are there any questions about von Kampen's theorem or this proof or the statement of von Kampen's theorem? I think it requires a little bit of time to digest the first time.
I guess this theorem, is it like, at least the second part, which I guess you'll talk more about, like, is it, I guess it's showcasing in like the topological sense that like, so I think maybe this was asked earlier, that can every group be associated to a topological space? And like, isn't every group like a quotient at least of a free group? So like in theory there is a space corresponding to every group?
Yeah, that's exactly true. But you have to describe how to construct your space.
Okay.
So this is the idea. This is the idea. Every group, as you say, is a quotient of a free group, right? So that means that every group, it's a very cool idea, by the way. So every group, that this is also formulated as every group has a presentation, right? So it's a free group with some elements generated by some elements, modulo some relations given by equations in these elements, right? That's what you just said.
Mm-hmm.
And then you look at these elements, the generators, and you first take like a, have you heard the word bouquet of circles?
Mm-hmm.
Right? You take a point and you put circles based on that point for each of these generators, right? That will turn out to be a free group. The fundamental group of that space will turn out to be a free group on that number of generators. But now you have to add the relations somehow. You have to impose them topologically. So how do you do that? You look at the relations, the things you quotient by, and there's a way of gluing a disk into this bouquet of circle so that you impose the relations on the fundamental group.
Okay.
So I will discuss this in more detail, and it's in Hatcher. But the idea is that you can construct, actually it's not too of a crazy space, right? You started with like loops on a point, and then you glue in a disk around these loops in such a way which determined by the relations in your group. You know, the relations say like some things are homotopic or something like that, and you use this two disk to make certain loops homotopic or certain elements in the fundamental group homotopic, in the free group homotopic. I'll explain this in more detail, but that's the idea.
So you couldn't necessarily like work backwards in like trying to define like a phi map and then saying like what the kernel, like artificially constructing it algebraically, I guess. Like you know what you want it to be, and you know what you want the kernel to be, right? Because if you have a free group, if you have any group and you write it as a free group quotient something, you should be able to like build the map that has kernel.
That's what you're doing. The problem is that you have to say what X is, right? That's what we want to construct. We have G, and we want to construct some X such that pi1 of X is G.
Yeah, I mean, yeah, I don't know if you can say what like U and V are.
Yeah, you can say what U and V are. And the idea is, I'll explain later.
Okay, that's fine.
Yeah. But you can read ahead in Hatcher. It's a good idea. By the way, I'm following Hatcher's exposition of von Kampen's theorem. It's more concise than Munker's. Any other questions? Okay, I'll see you on Monday. Let me know if you have any questions through email or if you want to meet. Okay? Bye. Have a good weekend.